Somewhere inside a particle accelerator, a photon made a decision it shouldn't have been able to make. It acted as if it already knew the outcome of an experiment that hadn't happened yet, as if the future had quietly reached back and rewritten the past. When physicists reviewed the data, they found something unsettling. The laws of cause and effect, the bedrock of everything we believe about time, had begun to crack. Across the scientific world, equations started whispering the same strange thing. In the deepest layers of quantum mechanics, time wasn't showing up at all. It simply vanished. Some called it a fluke of mathematics. Others saw it as evidence of a much bigger truth, that time might not be a flowing river at all, but an illusion our minds create to keep from drowning in something far stranger. And yet, the more we searched for time, the more it refused to appear. In black holes, it seems to stop. At the quantum scale, it appears irrelevant. And in the equations meant to unite gravity and quantum physics, it isn't there at all. But this story isn't just about equations. It's about what happens when everything we think we know about reality itself starts to unravel. Because if time doesn't exist, then the universe isn't moving forward. It's standing perfectly still. Every heartbeat, every memory, every future you'll ever live is already frozen. A mosaic of moments existing all at once. And hidden in that stillness is a quiet, unsettling possibility that physics has never been about describing motion through time, but about explaining how timelessness somehow feels like motion. In the next few moments, we'll follow the clues, from Einstein's collapsing clocks to photons that change their own past, to see why scientists now believe time might be an illusion, and why the truth behind it could rewrite everything we know about existence. But before we begin, if quiet stories like this help you drift through the strange beauty of the universe, I'd be deeply grateful if you'd help this small channel grow by subscribing. And if tonight's story about time stays with you, please give it a like or share what the idea of time means to you below. I always love reading them. So let's begin with a mystery that even the most careful minds still whisper about. A simple beam of light that seems to know the future before it arrives. How can a particle act as if a future choice already happened? A single photon heads into an interferometer. It splits into two possible paths, left and right, like a coin suspended in mid-flip. At the exit, we can decide whether to recombine the paths so they interfere, revealing wave-like behavior, or to mark which path it took, revealing particle-like behavior. In the delayed choice setup, that decision is made only after the photon has already moved past the paths. Yet the data line up as if the photon's earlier behavior depended on that late decision. Here is the twist that pulls this out of textbook territory. When we choose a configuration that preserves path information, the interference washes out. The pattern looks like individual particles hitting the screen. When we choose a configuration that erases path information, the interference reappears. The pattern shows the familiar fringes of a wave. The surprise is not that those two outcomes exist, but that the choice is made after the photons trip through the paths. It reads like a violation of everyday cause and effect. Later choices deciding earlier behavior. The delayed choice quantum eraser pushes this further. The setup uses pairs of entangled photons. One photon, the signal, travels toward a detection screen. The other, the idler, carries information that can, in principle, tell us which path the signal took. The key move is that we route the idler through devices that either preserve which path information or erase it, and we arrange those devices so the idler's fate is decided after the signal has already struck the screen. When we later sort the signal hits into subsets based on how the idler was measured, the subsets linked to erased path information show interference. The subsets linked to preserved path information do not. The Scully-Drool version is the canonical example. It uses atoms or photons and cleverly introduced markers that label the paths. Mark the paths and interference vanishes. Erase the labels coherently, and interference returns, but only when you condition on the matching idler outcomes. This conditional sorting is the heart of the result. If you look only at the raw, unsorted pattern of signal hits, you do not see interference. The fringes appear only when you group the hits by the idler's later measurement result. That is where the correlations live. Lab replications advance the timing control. In one experiment, researchers arranged distances so that the idler's detection choice happened long after the signal was registered. The apparatus included beam splitters on movable stages, path length delays, and fast switches. The alignment had to be precise down to fractions of a millimeter to keep the two alternative idler routes coherent. The signal detector recorded a broad distribution of spots as usual. Later, the computer matched each signal hit with its partner idler result. In the eraser subset, the spots lined up into fringes. In the which path subset, they filled in the gaps. The interference was there all along in the correlations, not in the raw screen. None of this allows communication backward in time. The no signaling principle remains intact. You cannot use the choice of idler measurement to send a message into the past or faster than light, because the signal's unsorted pattern carries no usable signal. Only when you combine both records, signal and idler, do the correlations show the pattern. That demands a classical channel to compare notes, which moves at or below light speed. The experiments go out of their way to enforce this, separating detectors so that events are space-like and using random choices to set the idler measurements. To keep it grounded, think of a story that was printed, shipped, and shelved. Later, someone edits a later chapter and a new edition comes out. In our ordinary world, the earlier chapters in the old edition stay exactly as they were. The quantum eraser feels like a case where an edit to the later chapter seems to change the earlier chapter when you place the pages side by side. But this is only an analogy. Nothing is physically rewritten. The change appears when you group the earlier pages with matching later pages in the new edition. The earlier pages alone never carried the hidden message. Timing control in these studies is not a flourish. It is the entire point. Engineers use synchronized clocks, fiber delays, and random number generators tied to physical signals. In some runs, the random setting that determines the idler's measurement is triggered after the signal detector has already fired, by a margin that, when transformed into light travel time, exceeds the separation between devices. This ensures the choice is not only late, but also space-like separated from the signal event. In that regime, any story about influences traveling at or below light speed cannot link the choice to the earlier hit. The correlations still line up. Groups have pushed the choice to cosmic distances. In cosmic delayed choice variance, the random setting that picks the measurement is derived from light arriving from astronomical sources. The photons that serve as random bits began their journeys billions of years ago. When those bits steer the apparatus in the lab, they ensure that any hypothetical mechanism that secretly set the experiment in advance would have had to coordinate with the cosmos on a grand scale. The outcomes still show the same pattern. Correlations that sort into interference or not, with no way to extract a signal from the unsorted data. So what do we make of a photon that seems to act as if a future choice already happened? The clean statement is this: the pattern in the joint data reflects correlations, not classical retrocausality. The mathematics of quantum theory predicts those correlations precisely. The wave function assigns amplitudes to joint events. When which path information is available in principle, the cross terms that would produce fringes cancel. When that information is coherently erased, the cross terms contribute and fringes return in the conditioned subsets. The decision does not travel backward. It is encoded in how the full experiment is arranged. Still, that clarity does not rescue our familiar timeline. The everyday story runs on ordered causes pushing effects along a single axis. The eraser experiments refuse to fit neatly. Here, the global configuration determines the correlations and the sequence we prefer to tell. First, the photon travels, then we decide what to do does not map onto a unique causal chain within the quantum description. The lab notebook shows events stamped with times. The theory matches those stamps with probabilities that care about which measurements are compatible and which are not, rather than about a single track of cause and effect. Consider how detectors are labeled and how coincidences are sorted. Each pair of entangled photons shares a tag. Electronics record arrival. Times within narrow windows. These coincidence windows define which signal hit pairs with which idler outcome. Change the path length by small amount and the phase shifts. The interference fringes slide accordingly within the conditioned subsets. This sensitivity to phase is why the apparatus is built on isolation tables, with temperature control and vibration damping. Tiny mechanical shifts translate into phase differences that either preserve or erase the delicate balance the interference needs. The urge to read a story of messages from the future is strong because our language is temporal. We talk about influences before and after quantum mechanics invites a different grammar. It speaks of joint probabilities, compatible observables, and constraints that prevent certain combinations from appearing. The no-signaling theorems are not patchwork fixes. They fall out of the same structure that gives the interference patterns. The forbidden thing is not influencing the past, but extracting a pattern from local data alone. Once both sides are compared, the joint pattern looks uncanny, but each side alone remains bland. This is why these experiments shook researchers. Not because they violated relativity or sent messages to yesterday, but because they made time feel like a poor guide to the structure of quantum events. If the relevant facts are about global arrangements and correlations, then the idea that the photon was a particle, or was a wave, as it moved through the apparatus, drops away. Those are properties of the whole experimental question, not of the single photon at a single time. The timeline we draw on the chalkboard is our bookkeeping. The quantum bookkeeping is different. The cosmic variants add a final nudge. If choices keyed to light from distant sources give the same outcomes, the conspiracy needed to rescue a classical timeline would have to be vast and ancient. Instead of hunting for such a mechanism, it is cleaner to accept what the equations have said all along. The interference lives in correlations among parts of the setup, and those correlations do not respect a simple one-way flow of cause and effect through a separate time parameter. All of this leaves a question hanging. If the outcomes are fixed by correlations in a way that sidesteps a neat timeline, what becomes of cause and effect? Perhaps cause and effect are not primary at the quantum level. They emerge when we coarse-grain many events and treat records as if they were states marching forward. At the level of single photons and entangled pairs, what we call before and after do not carry the load. The lab's result is a clue. Our classical timeline is not a reliable guide inside quantum mechanics. There is a payoff in accepting that. You stop trying to force the data into a story of influences darting backward and forward. Instead, you look for structures that constrain which joint outcomes can and cannot occur. Those structures are real and testable. They produce numbers on screens that match predictions with impressive precision. They leave intact the speed limit on signals and the rules of relativity. They also hint at a deeper layer where time is not the arena but part of the score we write when we listen to the system in a certain way. That turn sets up the next step. In the lab, our sense of before got tangled. In the math, something even stranger happens. The very equation that tries to weld quantum theory to gravity refuses to include time at all. The symbol we expect to guide evolution is missing. The universe's state sits there, silent, with everything encoded at once. from a lab mystery to the equation that erased time itself. What happens when the master equation for the entire universe has no time in it at all? Not hidden in a corner, not waiting in a subscript, gone. You scan the symbols expecting a clock somewhere, a T to anchor motion, and there's nothing. The equation insists on a universe described all at once, like a photograph that contains everything it needs without a shutter speed. That absence isn't a typo. It's the feature that turns the usual story of physics on its head. Here's how it arrives. Start with general relativity, where gravity isn't a force but the shape of space-time. Translate that smooth geometry into the language of quantum theory using a step-by-step recipe called canonical quantization. In that process, the ingredients of Einstein's theory become operators, and the allowed states must satisfy constraints that enforce the freedom to choose coordinates. Among those constraints sits the Hamiltonian one, the piece that in many theories would generate evolution. In this construction, it doesn't move the universe forward. It equals zero. Apply that to the quantum state meant to describe the entire cosmos, and you get a single condition. The state is allowed only if the Hamiltonian constraint annihilates it. No external time parameter shows up, because coordinate choices, diffeomorphism invariance, have stripped away any privileged clock from the start. That leaves a striking object, a wave function of the universe that doesn't evolve in time. It sits there, encoding possibilities and their weights, yet never stepping from one moment to the next. The usual playbook of quantum mechanics, where a system state depends on time and changes according to an equation of motion, falls quiet. The master equation tells you what is true, not when. You can ask what correlations the universe contains, but not how those correlations march along a background tick-tock. The tension is immediate. A framework built to combine gravity and quantum rules seems to deliver a static answer where motion and change must be explained without pointing to an external clock. What then does this static object actually describe? Think of it as a catalogue of relationships. Every part of the universe, fields, matter, geometry, appears not as a sequence through time, but as a set of interlocking patterns. The wave function encodes the probability structure of those patterns. If one region has a particular field configuration, what is the likely shape of geometry nearby? If one variable takes a certain value, how do others correlate with it? These questions have precise answers in the static state. There is no time variable in the equation, but there is structure in abundance. The absence of a ticking symbol doesn't erase everything we care about. It reorganizes it into a single, timeless object that compresses the full network of correlations into one condition. This is not an accident caused by a careless derivation. The zero-value Hamiltonian constraint is baked in by symmetry. General relativity allows you to relabel coordinates freely without changing physics, and any supposed time variable defined by labels alone would be arbitrary. The quantum version must respect that symmetry. So the master condition removes any absolute clock from the equation by construction. If you find yourself reaching for a stopwatch to make sense of the state, the theory replies that you brought that stopwatch from outside, and it doesn't belong. To make that concrete, set aside philosophical labels and focus on the mathematics of constraints. In the canonical approach, physical states are those that satisfy all the constraints, spatial ones that enforce how slices of space can be reshaped without effect, and the Hamiltonian one that enforces reparametrization of the slicing. Solve them, and you land on the allowed space of states that capture geometry and matter together, with no leftover parameter to call time. The result is often described as a timeless wave function, a global object containing the universe's full probabilistic content. In this interpretation, the lack of a time symbol isn't a gap to be filled later with a patch. It is the sign that a different kind of description is required. Here's an analogy that fits the shape of the problem. A musical score contains every note and every harmony in a piece. It's all there at once on the page. Nothing in the ink itself is playing. Performance shows up when a musician relates measures to each other in sequence. In the timeless equation, the score is complete. The performance, what we call dynamics, has to be drawn out from relations internal to the score, not from a separate metronome imposed from outside. Your sense of tempo comes from how phrases fit together, not from a stopwatch sitting on the piano. Researchers reviewing this framework have labeled the whole puzzle the problem of time. It shows up wherever you try to treat the universe as a quantum object while respecting the symmetry principles that made relativity successful. Multiple proposals aim to resolve it. Some look for an internal clock, a physical quantity among the variables that can serve as a reference against which others change. Others step further and treat time as an emergent feature, a byproduct of entanglement and coarse graining rather than a base ingredient. The debates compare these routes, test their consistency, and map the consequences for cosmology and black holes. What unites them is acceptance of the starting point. The master equation itself does not carry an explicit time parameter. So if the universe's fundamental description is static, how do motion and change return? The key is to trade absolute evolution for conditional statements. Ask, given a particular value of one variable, call it the clock degree of freedom, what are the probabilities for the others? Conditional probabilities already live inside the static wave function. They tell you, if this part looks like a dial reading 5, what distribution should you expect for the system you're watching? String those conditionals together across values of the clock variable, and you get the appearance of evolution without an external time parameter. The dynamics become relational, a choreography of parts measured against each other. It helps to parse the difference between a global silence and local stories. The global state does not move, but within it are consistent patterns that, when read along one variable, form sequences that look like motion. Pick a subsystem and designate it as a clock. Then track the conditional distributions of another subsystem as the clock's variable changes. The structure you recover matches the familiar equations that govern evolution in ordinary quantum theory, but only relative to that chosen clock. Switch clocks and you'll rewrite the story without violating the global constraint. The appearance of change rests on correlations, not on a universal tick. Even the interpretation of observables shifts. In ordinary quantum mechanics, you ask for the value of an operator at time t. Here, you replace that with questions about correlations. What is the likelihood that one variable has value A whenever another, designated as a clock, reads value B? These statements are meaningful, testable in their principle, and extracted from the timeless state without contradiction. They also reflect the underlying symmetry of the theory, since no single variable gets promoted to true time for free. This reframing also answers a practical worry. If the wave function is static, do predictions become impossible? Number. The static description produces the same kind of statistical forecasts as any quantum theory, but organized as relationships. Instead of evolving a state forward in time, you compute conditional amplitudes and probabilities relative to reference variables that play the role of clocks. The content is robust precisely because diffeomorphism invariance forbids the theory from depending on an arbitrary external parameter. In that way, the symmetry that erased time secures the consistency of prediction. The picture carries costs. You must accept that global simultaneity of all information lives in the state, and that what you call now is a slice you carve out by choosing a clock-like variable and reading off relations. You must also accept that different choices lead to different notions of evolution that nonetheless agree on invariant facts. These are not flaws tacked on to save the framework. They are the consequences of taking general relativity's lessons seriously while quantizing. The payoffs include a path to reconcile gravity's coordinate freedom with quantum theory's probabilistic structure without smuggling in a background time. Critiques of this picture often ask whether the elimination of time is a mere artifact of the chosen formalism. Would a different route to quantum gravity keep a time parameter alive? The answer layers nuance on nuance. Some approaches reformulate the constraints, some reorganize variables to highlight internal times more explicitly, and some explore emergent order from information-theoretic principles. Yet across reviews of these attempts, the core issue remains. Building a fully consistent theory with a privileged external time variable tends to clash with the symmetry structure that makes relativity tick. Even when an internal time is identified, it acts as a derived quantity, not a fundamental background. The musical score analogy stretches a bit further and helps anchor the intuition. The beauty and coherence of a piece doesn't come from the passage of a clock's second hand. It comes from the relationships among notes, intervals, motifs, progressions. Performers can choose different tempos and still reveal the same structure. Likewise, the timeless wave function carries the intervals and harmonies of the universe's variables. What we call motion is the act of reading those patterns along chosen directions. Change is not bolted on from outside. It's the way parts cohere. This is the mini payoff. The silence of the equation does not forbid dynamics. It relocates them. Motion reappears as relations among parts of a whole. The experience of evolution, the advance of hands on a clock, can be recovered as a sequence defined within the state, not as the state riding a universal timeline. You get back cause and effect-like orderings as constraints on allowable correlations, rather than as flows against a rigid background. The global stillness contains local movement stories. If that is the right way to read the universe's master equation, it sets up a natural next move. If change is relational and clocks are subsystems that we read against others, there's a candidate for how to build time from pure correlations. You do not attach a stopwatch to the universe. You pick one part and let entanglement with its partner do the counting. Can a universe without time still have ticking clocks? The idea sounds self-contradictory until you change what you mean by a clock. Instead of a device counting seconds against an external timeline, a clock can be a quantum subsystem tied to another by correlations. Time then isn't a backdrop, it's a relationship. That's the move known as the Page-Wouters mechanism. The whole state of the universe is static, but inside it, one part can act as a reference for another, and relative to that reference, change appears. If you step outside and look at the total state, there's no evolution anywhere. Step inside and condition on a clock reading, and motion shows up the way a melody appears when you read notes left to right. The setup is straightforward in principle. Split the universe into two parts, a clock and a system. Entangle them so their states are tightly linked, then define time by asking questions of the system conditioned on the clock showing a certain value. The global state satisfies a constraint that forbids any external tick, which means nothing moves as a whole. But when you slice the correlations according to the clock's outcomes, the system's statistics change in a way that matches ordinary evolution. No external meter is needed. You only need the map of how clock and system point to each other across the joint state. If the whole is static, why do parts look like they evolve? Because evolve becomes a statement about conditional probabilities. Given that the clock says 1, the system looks like this. Given the clock says 2, the system looks like that. The pattern across all clock labels recreates the smooth drift that we'd normally call dynamics. So, we replace an absolute timeline with a rule for reading slices of a static object. That raises a practical question. Does any of this show up in the lab, or is it just a clever change of words? A group in 2013 put the idea into practice with entangled photons. They prepared a pair in a way that, from the outside, looked frozen. The joint state didn't evolve globally. One photon played the role of a clock, the other played the role of the system. The researchers measured the system photon relative to outcomes on the clock photon. When the clock registered a particular outcome, the system's measurement statistics matched what you would expect if it had been evolving under a simple rule. Time showed up only when the outcomes were compared, not when the pair was considered as a whole. The mechanism did what it claimed. Change emerged from correlation, not from an external parameter sliding forward. What mattered was the conditional structure. You don't assign a t to the system. You ask, if the clock is found in state K, what is the probability distribution for the system's outcomes? Line those conditional distributions up by the clock's sequence of outcomes, and the system traces the same pattern as a standard Schrödinger evolution. The math reduces to a chain of conditional amplitudes that, when stitched together, reproduce the familiar wave-like progression. The trick is that the stitching is done by measurement on the clock, not by a hidden time variable running in the background. Think of two dancers in a single photograph with a series of faint overlays. If you scan across one dancer's poses in order, the other dancer seems to move with them. Nothing in the photo is actually moving, but your rule for scanning creates the effect of motion in the partner. Change is in the reading path, not in the raw image. The Page-Wouters setup works the same way. The joint state is the still image. The clock's ordered outcomes define the scan. The system's apparent motion is how the other dancers' poses line up under that scan. The 2013 demonstration wasn't a one-off curiosity. Follow-up work extended the dimension of the clock subsystem, allowing a richer set of ticks rather than a simple two-state flip, and tested how errors accumulate when the clock is noisy. As the clock's Hilbert space grows, you can approximate smoother and longer revolutions before imperfections blur the pattern. When the clock is small, the sequence of conditional states looks choppy, like a low frame rate video. Increase the clock's dimension and the motion smooths out. Researchers also characterized how imperfections in entanglement reduce the clarity of the apparent dynamics, providing error budgets that quantify when the illusion of time stays sharp and when it washes out. The key insight is that conditional probabilities can produce an effective Schrödinger equation for subsystems. You can write the global state so that the clock's basis labels the time and the system's relative state changes across those labels as if it had evolved under a Hamiltonian. Measure the clock in that basis, and you find the system looks like it has advanced a step. Skip a few labels, and it looks like it has advanced several steps. The feeling of a timeline emerges from the bookkeeping of correlations. If you drop the conditioning and look at the density matrix of the whole, the advance vanishes. This makes the idea of a clock less mysterious and more technical. A good clock in this framework is a subsystem whose states are well distinguishable and strongly correlated with distinct states of the system. It must be entangled enough to anchor clear conditional slices, but also readable without wrecking the pattern. The trade-offs are the same ones faced in any measurement problem. More precise readouts risk more disturbance. Noise in the clock blurs the system's apparent path. Experiments mapped these trade-offs by varying measurement strengths and quantifying how closely the conditional sequences matched a target evolution. There's also a limit to how far the description can go without drift. Because real clocks have finite dimension and imperfections, the conditional evolution deviates from the ideal as you read further along the clock labels. The error analysis showed where the deviations begin to dominate and how they scale with entanglement quality and readout resolution. What looks like a smooth march can wobble if the clock's internal structure isn't well matched to the intended dynamics, a reminder that time in this sense is only as clean as the correlations that define it. These details matter for an obvious reason. If time is relational, Anything that perturbs correlations can slow, speed, or scramble the apparent evolution. That means gravity, which affects phases and frequencies, should influence clocks not just by running them fast or slow, but by reshaping the correlations they rely on. Even tiny differences in potential could alter the phase relationships that make the conditional pattern line up, shifting where the ticks land when you read the clock's basis. The Page-Wooter's view doesn't replace the idea that gravity changes rates. It suggests a deeper layer where gravity may also change how the relational ticks arise in the first place. It also reframes what we mean by an observer. In this picture, an observer is another subsystem that reads the clock in the system and assembles a narrative by conditioning on outcomes. Two observers, who use different clock bases, could disagree about the sequence that best compresses their data, yet both sit inside the same global stillness. The preferred flow isn't handed down by the universe. It emerges as the best relational coordinate to track correlations in a particular context. The more reliable and higher dimensional the clock, the closer the effective flow matches a smooth parameter. This way of thinking connects to practical tasks. In quantum information settings, you often lack a shared reference frame. Parties establish one by exchanging entangled states and conditioning on agreed measurements. The Page-Wooter's mechanism describes how you can simulate evolution without a shared external time by treating one part as the clock and another as the system. The quality of communication depends on how sharply those conditional patterns reproduce the target dynamics. Error models from the photonic experiments show how misalignment and noise degrade that performance and how to calibrate around it. It also bridges to foundational puzzles. If there is no global T, you don't ask why the universe chose this rate rather than that rate. You ask why certain subsystems are good clocks. The answer points back to entanglement structure. Systems with evenly spaced energy levels and stable phase relationships make cleaner relational coordinates. Systems with irregular spectra or strong noise make poor clocks. The distribution of good and bad clocks and how they couple to the rest could shape the macroscopic sense of a uniform flow that we rely on every day. The mechanism sits comfortably with the earlier lesson that our classical timeline misleads us in quantum contexts. You don't need a photon deciding its past to produce strange-looking before and after. You only need correlations that are read in different bases or at different stages. Condition on one reading, and a system looks wave-like. Condition on another, and it looks particle-like. The timeline you thought was fixed is just one way of slicing a static joint state. The Page-Wooter's move turns that observation into a constructive tool. Use a clock subsystem to define a consistent slice where motion appears. There's a quiet payoff here. A static universe can host moving stories provided motion is read as a relationship among parts. The global silence doesn't stop local music. The score contains every note at once. But if you focus on a particular line and index it by a reliable clock, the melody unfolds. If clocks are correlations, then anything that shapes correlations shapes the ticks we hear. Gravity does that by bending phases and frequencies, so the next step is to see how the very curvature we live in nudges the tempo of these relational songs, and how that shows up in devices we trust every day. Why does your phone's map keep you on the right street only if satellites above Earth correct their clocks every single day? Because in orbit, a second stops meaning the same thing it means down here. Those satellites move fast and sit higher in Earth's gravitational field, and both facts change how their onboard clocks tick. If the system didn't account for that, your pin would drift more and more with each passing hour. By the end of the day, you'd be tracking a version of you that's wandered far off the road. Step back. Newton thought of time as absolute, steady, universal, the same for everyone. Relativity replaced that picture with spacetime, where gravity is geometry and time is woven into the shape of the world. Move faster, and your time stretches. Climb out of gravity's pull, and your time loosens. The clock you carry is not a neutral referee. It's a device that responds to motion and mass, following curves drawn by the universe itself. This isn't philosophy tucked into equations. It's hardware and software running on satellites that circle Earth. Relativity gives two competing nudges to time, one from speed and one from gravity. The satellite's speed makes its onboard clock slow down relative to an identical clock on the ground. But its higher altitude and weaker gravity makes that same clock speed up. The system has to include both effects to keep every timestamp honest. That tug of war is the reason the engineers preload and continually correct satellite clocks, so what the system calls now stays aligned across the planet. Here's where it gets tangible. The velocity effect subtracts a handful of microseconds from each orbiting day. The gravity effect adds a larger handful. The net tilt favors faster ticking aloft by a few dozen microseconds per day. That margin sounds tiny, but GPS depends on nanosecond-level timing. If the satellites let that difference accumulate, the location signals would slip. After many hours, the error would balloon. Over a day, your device would point you to the wrong block, then the wrong neighborhood. It would miss freeway exits, misplaced delivery trucks, and wobble through maps like a compass next to a magnet. The basic method is simple in concept. Your receiver listens for time-stamped pings from several satellites. Because light takes time to travel, those pings arrive offset by tiny delays. From those delays, your receiver triangulates your position. But the method assumes every clock involved agrees on what a second is. If an orbiting clock runs a little fast or slow relative to the ground clocks, the distance that your receiver infers becomes a little wrong. Stack that error across several satellites and over time, and the math points you to the wrong place. When engineers fly clocks to test these ideas, the results line up with relativity. Airborne clocks, carried around the world on jets, register the effects of speed and altitude. The differences are small, but they show up when you compare the airborne clocks to the ones left behind. You can even measure gravity's influence on frequency without leaving a building by comparing signals from different heights. Radiation climbing up or down a gravitational gradient shifts in frequency by a tiny, predictable amount, reflecting that time runs differently across floors. Today's optical clocks push this further. Move one a step higher, and the frequency shift ticks noticeably if your instrument is sensitive enough. Floors aren't timelines, but their elevation is enough to bend the clock just a touch. Think of time in relativity as a metronome that flexes. Motion tugs it one way, gravity tugs it another. Change the tempo, and everything that depends on that tempo must adjust. GPS folds this into its design. On board, the clocks don't run at the factory rate. They run at a rate pre-calibrated so that once the satellite is moving and feeling less gravity, they tick in sync with the ground network. Even then, the Earth's shape, its rotation, the satellite's route, and periodic maneuvers all tweak the local tempo. Ground control uplinks corrections. The system blends all of that into the time solution your phone swallows whole. The numbers matter. The velocity-induced time loss in a day is measured in microseconds. The gravity-induced gain is larger, also in microseconds. Subtract one from the other, and you land at a net daily offset of a few dozen microseconds. That doesn't sound like much until you turn microseconds into distance. Light travels about 300 meters in a microsecond. Leave several dozen microseconds uncorrected, and you misplace a signal by kilometers. Navigators would be steering ships toward shoals they can't see. A rideshare would think you're waiting in the next neighborhood over. The system only works because its architects took relativity as an engineering requirement, not a philosophical curiosity. We've tested the pieces in other ways. Drop a beam down a tower and measure its energy at the bottom versus the top. Oh, and you'll see the predicted shift. Tiny, but real. carry a cesium or rubidium clock across latitudes, altitudes, and speeds, then compare it to a reference clock on return, and its record of elapsed time will disagree by exactly the pattern predicted. Swap the old standards for modern optical clocks, and the experiments tighten. Two devices, one floor apart, can now sense gravity's tempo change with startling precision. The effect isn't exotic. It's part of everyday space around you. You can even see the stakes for timekeeping systems outside of satellites. Earth doesn't spin perfectly evenly. Tides and other factors nudge its rotation. The time we live by has to reconcile slow drifts in the planet's turn with the steadiness of atomic standards. Those adjustments ripple through networks, computers, and markets that depend on consistent timestamps. When we insert tiny corrections into the global time count, some systems stumble if the software assumes time should always tick forward in the same rhythm. That fragility shows how deeply we rely on well-defined seconds and how slight irregularities can cascade. All of this turns a simple idea, time passes, into a careful statement about motion and gravity. There is no single, universal flow. There are many local flows stitched together by rules. A second on the ground is not strictly equal to a second in orbit. Yet the architecture of modern technology assumes we can keep those seconds coordinated. The success of navigation, finance, and communication hinges on treating relativity not as a curiosity, but as the clock on the wall. Here's the twist that sets up the deeper conflict. In relativity, time is elastic and woven into geometry. It's a coordinate you can transform, bend, and dilate. In quantum theory, time is a parameter the equations refer to, a background label the wave function evolves against. Quantum mechanics usually treats time like the stage manager who never steps on stage. It doesn't make time a dynamical quantity with its own uncertainty in the way position and momentum are. That split is not just a stylistic difference. It becomes a chasm when you try to write a single theory that respects both. GPS exposes one side of the chasm. We can fold relativity into a functioning system, and the world lines across the sky tell your phone where you are within meters because the designers bowed to a flexible clock. But ask those same equations to guide a single framework that also respects quantum indeterminacy, and you find mismatched assumptions. Relativity tells you clocks lengthen and shorten depending on their path through space-time. Quantum mechanics asks you to evolve a state through an external time variable that doesn't get bent by anything. Put the two into the same conversation and the grammar breaks. The mini payoff here is simple and unsettling. Relativity bent time, made it local and contingent, and demanded that engineers treat it that way. Quantum theory, as usually written, puts time off to the side, a parameter, not an observable thing. We can build machines that prove both views hold power, but the difference in how they place time deepens the conflict. One theory reshapes time, the other uses it as scaffolding. You can see why a single picture keeps eluding us. So we aim toward a meeting point, a language where time dissolves as a master clock and returns as structure, correlation, and constraint. The satellites tell us clocks are flexible. The lab tells us that evolution can be relational, not absolute. The mismatch sets the stage for a radical idea. Maybe time is not something the universe has, but something that emerges from how its parts relate. From here, we turn from the elastic metronome of relativity to theories that treat motion as a story we read out of a still score, where the ticks come from patterns rather than a universal beat. What if reality is a gallery of still frames with no projector? That's the claim from Julian Barber's radical proposal. Time is not a thing that flows, but a feeling that arises when we move through a collection of static configurations. He calls the total collection Platonia. Each configuration is a complete now, containing the positions and relations of everything, with no thread tying one to the next. The thread is our own construction. We stitch certain pages into a sequence and call that sequence a life, or a history, or a cause, followed by an effect. In this view, the projector is in our heads. The film is a library of frames that already exist. Barber's approach builds on a simple but sharp idea. Time is an abstraction that we deduce from change. He points to a minimal model of 3 particles. Each triangle formed by those 3 points is a self-contained instant, a full description without a clock. If we place those triangles next to each other and read a trajectory, we feel a flow of time. But the flow comes from our act of arranging shapes, not from a ticking external variable. Extend the idea to the universe. Replace 3 points with all matter and fields. The basic objects are not moments passing, but shapes relating. From that starting point, Barber develops shape dynamics. Instead of tracking how distances scale or where a system sits in space, he focuses on the pure shapes defined by ratios and angles. Scale drops out as inessential. What remains are configurations you can sort by their internal structure, independent of a ruler. In Platonia, these shapes fill out a space of possibilities. There is no master parameter marking before and after. There are only relations between configurations, and constraints that carve out which relations count as lawful. The immediate objection arrives quickly. If there is no flow, what grounds memory or cause and effect? Barber answers by looking at structure inside the nows. Some nows contain records, correlations that encode traces of other nows. A brain state that stores a footprint, a tree ring that encodes a drought, a fossil embedded in rock. These records live within a single configuration. They do not require a pre-existing timeline. They require patterns that point consistently to other patterns. In practice, the configurations that resemble our world contain abundant records that align so we experience a coherent story. To make this concrete, he studies complexity. Define a measure that is independent of scale, sensitive to how matter clumps. For a set of particles, complexity grows when structure forms. Closer clusters spike the measure. Dispersed arrangements lower it. In this language, a uniform, featureless arrangement counts as low complexity. A richly structured cosmos reads as high complexity. Complexity, not an external time, orders the gallery in a meaningful way. This leads to the Janus point. Take the entire configuration space and identify a special region where the complexity is minimal. From that middle, complexity increases in 2 directions. Each direction corresponds to what observers, embedded in the respective sets of configurations, would call their future. They each see an arrow pointing away from the low complexity center. No global time is required. The arrow emerges because records and structure accumulate as complexity grows. Memory appears in nows on either side as an asymmetry in stored information. More records of simpler, past-like configurations, fewer of more complex future-like ones. In a simple 3-body model, you can watch this happen in the mathematics. When the particles drift into a more symmetric, spread-out triangle, complexity dips. As interactions pull certain pairs closer, the shape becomes more distinctive. The complexity rises. That rising complexity correlates with the growth of identifiable structures, stable relationships that can carry records. Scale never enters as a fundamental unit. The story depends on shape alone. So in Platonia, a sense of past and future is a statement about which nows contain patterns that encode other nows more or less compressed, not about which nows come earlier or later. Think of it as a library of snapshots. You walk the stacks and notice some pages contain references, citations, photographs, echoes of other pages. If those references form a consistent network that points towards simpler pages with fewer references, you infer a direction. The direction is the gradient of reference density, not a current flowing through the books. The plot is the pattern linking related pages, not a force pushing you from cover to cover. That's how memory can arise without a river of time. It's the presence of internal records that align along increasing complexity. This picture raises hard questions about thermodynamics. The second law says entropy tends to increase. If plutonium is static, how do we recover that trend? Barber argues that the second law's usual statement depends on boxed systems and certain boundary conditions. In an unconfined universe with long-range interactions, structure formation can increase a meaningful measure of complexity even as local entropies behave differently. The emergent arrow follows the rise of structure and the proliferation of records. Critics push back, asking whether this complexity simply reframes entropy with new labels, or whether it really grounds the familiar thermodynamic behavior. Barber responds that his measure is scale invariant and hypersensitive to clustering, making it suited to gravitational systems where the standard entropy intuition from gases in boxes misleads. The debate centers on whether this shift preserves the predictive success of thermodynamics while explaining the arrow without a global clock. Another criticism targets causality. If all nows exist in Plutonia, do causes vanish? In this view, causality becomes a mapping between patterns. A cause is a stable relation such that configurations with structure A reliably coexist with records of structure B that fit certain dynamical constraints. The law is then a constraint on allowed adjacency in configuration space. What kinds of patterns co-occur and how often? It reframes causes as statistical regularities across the gallery. The payoff is clarity about why retrocausal paradoxes don't appear. There is no flowing chain to send a message through. There is only the requirement that configurations with particular records fit the same consistent network of correlations. The Janus point adds a further twist. If complexity increases away from a central low-complexity slice in two directions, then observers on each side would define opposite arrows. Neither arrow is global. Each is local to a branch of configurations where records accumulate. This avoids the need to postulate an improbable initial condition at the beginning of a universal timeline. Instead, the universe's beginning is a structural feature of configuration space, a region of minimal variety, from which variety grows. Observers never meet their counterparts across the divide because their records and structures embed them within one arrow or the other. Return to the library analogy. Suppose the stacks include a narrow aisle of minimalist pages, sparse on references. Moving away from that aisle in either direction, pages grow denser with footnotes, cross-references, and indexes that point back toward the sparse ones. You and I live in a wing where references overwhelmingly point toward the aisle, so we call that direction the past. Someone on the opposite wing would agree on the structure but disagree on which side counts as past. Neither needs a clock to make sense of their history. The arrow arises from the asymmetric distribution of records. Barber's insistence on shape over scale also shifts how we think of deep laws. If most physical observables can be recast as relations among shapes, then many supposed absolutes become gauge, redundant labels we can remove. In that language, the true content of the laws are constraints on what counts as a valid configuration and on which configurations sit near each other in the lawful web. Dynamics, as we normally think of it, is the inference we draw when we trace a path through this web along increasing complexity and coherent records. The implications for everyday intuitions are stark. Memory is not a beam moving forward, it is a fact inside a now. Anticipation is a pattern inside a now about other nows that fit with current records. Regret and cause are also static relations. We are not sliding along a timeline. We are located within a configuration whose internal structure includes the story we tell as movement. That does not empty life of meaning. It changes where we place it, in the richness of structure and the consistency of the record network, not in a metaphysical flow. Still, one question cuts through. If every frame exists in Platonia, do all moments coexist equally? Barber's answer is yes, but coexistence here means inclusion in the gallery, not interaction across a current. The tension we feel about choice, about agency, shifts to the structure of which configurations exist, with which records of decision-making processes and outcomes. The patterns that we call deliberation and commitment appear in nows that align along rising complexity, so we experience agency as part of that alignment. This grants a mini payoff. Causality, in this view, is pattern recognition across configurations. We extract laws by noticing that certain shapes come bundled with records of other shapes in consistent ways. We call that a causes B, but nothing flows. The reliability we lean on is the stable architecture of Platonia, not a procession. To see how this differs from relativity's take, we need to set Barber's gallery next to block universe variants. In relativity, the block is spacetime, a four-dimensional structure where events are laid out with metric relations. In Platonia, by contrast, the block is a space of shapes without a built-in time dimension. One organizes events as correlations inside configurations. The other organizes them as points in a manifold with light cones. The next step is to weigh these blocks against each other and see where they agree, where they diverge, and how each handles the puzzle of a universe that feels like it's moving. Does the universe already contain your future, or is it still being written? That question sounds like philosophy until you try to place it on a space-time diagram and realize the diagram refuses to pick a single global now. One observer's presence slices through events that, for another observer moving differently, sit partly in what they call the past and partly in what they call the future. That clash is not a trick of language. It is baked into how velocities and gravity shift the coordination between space and time. So we need a map that can handle competing nows without breaking. Several maps exist. Each makes different claims about what is real. Start with the block universe, often called eternalism. In this view, reality is a four-dimensional whole. Events are laid out across space-time the way cities lie across a landscape. Your birth, your next birthday, and the last message you will ever send all sit in the block. They do not wait to pop into existence. They are located. Our experience of the present, in this view, is the mind's way of being situated at a particular region in the block, not evidence that only that slice is real. Then there's presentism, which says only the present exists. The past has slipped away. The future is open. It aligns with how daily life feels, but it strains against relativity's insistence that present is not absolute. Finally, the growing block tries to split the difference. The past and present are real, but the future is not yet on the ledger. The block expands as new moments join the record. Each option forces a trade-off. Eternalism keeps peace with relativity. There is no universal now to violate, but it inherits a difficult question. If the future already exists, what is the status of choice? Presentism preserves a robust sense of becoming, but it clashes with the relativity of simultaneity because observers in relative motion do not agree on which distant events share your present. The growing block preserves an objective present and an open future, but it has to define how the edge of reality moves through the block without leaning on a global clock that relativity denies. The tension lives in those details, not slogans. Space-time diagrams make the issue concrete. Draw your world line as a curve through the diagram. Draw another world line for a fast-moving spacecraft. For you, a horizontal slice might pass through a supernova you call present. For the spacecraft, tilted slices of present will intersect different events. Neither slice is privileged by the laws. If you try to impose a single, universal slice, you have to pick a convention that hides the fact that no experiment can detect that choice. That is the heart of the challenge to a universal now. So where does the arrow of time come from in a block that does not flow? The answer many scientists turn to is the past hypothesis. The early universe began in an extremely low entropy state. Entropy counts the number of micro-arrangements compatible with the large-scale facts. A low number means extraordinary order and limited options. From such a start, typical evolution leads to higher entropy because there are overwhelmingly more disordered arrangements than ordered ones. On a block view, the arrow is not a force that pushes. It is a pattern across the block. Past regions have lower entropy. Future regions have higher entropy. That pattern explains why traces, memories, and records point one way. We have reliable records of lower entropy states and not of higher entropy states, because records themselves are low entropy structures formed when entropy increases elsewhere. This also reframes choice. In a block, your decision at noon tomorrow is part of the block. But the chain of microstates that encode your deliberation, your uncertainty, and the information you consult also lives in the block. Calling it predetermined smuggles in a second time that runs outside the block to fix things in advance. There is no outside timeline here. Agency shows up as structures in the block where options are evaluated, predictions are computed, and actions connect to outcomes. In the growing block, agency carries a different shade. The future is not yet real, so making a choice is tied to how the block grows. You still need a rule about growth that does not contradict relativity. Without that, growth becomes metaphysical decoration. Even the quantum form of the arrow ties back to initial conditions. The past hypothesis restricts the possible microstates early on. That restriction picks out a small subset of histories where macroscopic entropy rises. In daily terms, that is why cream mixes into coffee and not the other way around. On the block view, both mixing and unmixing exist as allowed microdynamics, but only histories consistent with the low entropy boundary contain robust records and observers who remember the past rather than the future. Retrocausal interpretations add another layer. The two-state vector formalism treats quantum systems as constrained by boundary conditions at both ends. One vector evolving forward from preparation, and another evolving backward from measurement. The transactional interpretation speaks of offer and confirmation waves that meet. These ideas do not license paradoxes like sending a message to your former self. They change how we assign causes and how we narrate events without changing the observed statistics. The appeal, for some, is that they restore symmetry in the laws while letting arrows arise from boundary conditions, not from asymmetries in the equations. In a block, those boundary conditions are just features of the four-dimensional whole. Think back to the atlas analogy. In eternalism, the atlas is complete. You can open to any page. The routes between cities are drawn. Your trip is a path across pages. The growing block is an atlas with new pages being added at the edge of what is charted. You can still plan routes, but some destinations do not exist yet. In presentism, there is only the current page. Past pages are gone. Future pages are blank. Each atlas changes how we talk about responsibility and hope. In the complete atlas, responsibility is local. Your choices shape the path on the page where they occur. Their effects appear down the route because that is what it means for them to be your choices in the first place. In the growing atlas, responsibility includes shaping which page gets added next. The metaphors are simple, but they echo the technical constraints we have to respect. The relativity of simultaneity undercuts any hope of defining a global edge cleanly. You can define a foliation, a way of slicing the block into times, but you must accept that it is a choice of description. Observers tied to different motions adopt different foliations, and the physics stays the same. That is why block views feel so natural within relativity. You do not need a global clock to talk about invariance. You refer to intervals along world lines and light cones that everyone agrees on. Entropy stitches an arrow onto that fabric. Start with a low entropy boundary and let typical dynamics run. Records, memories, and causes align in one direction. Try to flip the arrow, and you quickly need miracle-like correlations between current micro-states that would erase records and unbreak broken eggs. The past hypothesis makes such conspiracies vanishingly rare by assumption. That assumption is not arbitrary. It compresses the many facts about the early universe's smoothness and uniformity into one statement about order. Quantum ideas that allow influences from both temporal directions remain consistent with that arrow because they do not permit signaling to the past. They only change how we compute probabilities across pre- and post-selected ensembles. That still fits inside a block that hosts forward and backward pointing constraints at its boundaries. The stories we tell about causes become two-ended. Events can be explained by what came before and by what is fixed later. But the practical arrow we live with, the one that guides planning and learning, still points from records to targets because records are formed in the low to high entropy direction. The sticking point for many is meaning. If the block is complete, why strive? The answer depends on where you place values. In a complete atlas, a difficult climb and its summit exist on their respective pages. The effort does not lose meaning because the pages already exist. The meaning is the structure that connects them. The training sessions, the decisions to continue, the moments of doubt and resolve. Those live in the same block. Saying they already exist does not separate you from them because already smuggles in an external time that the block denies. Your lived present is not late to its own party. If instead you favor a growing block, the open future is where value breathes. The worry then is how to keep that openness honest, while physics keeps telling us that no single slicing earns special status. Some versions try to anchor growth to local processes, letting regions add to reality based on causal structure rather than a global tick. That keeps the spirit of relativity better, but it also blurs the intuitive line between present and not yet. These metaphysical pictures do not change the empirical data. They map the same terrain with different legends. Eternalism highlights consistency with relativity. Presentism highlights lived experience. The growing block tries to keep a stable past and a genuinely open future. Each must answer to entropy's arrow and to quantum rules that, in some readings, refuse to keep causation one way. If arrows are emergent from boundary conditions and coarse graining, then the brain's arrow may be emergent too. The sense of a moving now, the alignment of memories pointing back and expectations pointing forward, could be the mind's way of riding the entropy gradient written into our local part of the block. That brings the question down from spacetime to the nervous system. If the universe does not supply a universal now, maybe the mind constructs one from signals that arrive with different delays and from predictions that fill gaps. The map of time inside your head might be an atlas. The brain edits continuously, stitching pages so the route looks smooth. The physics allows multiple consistent stories about what exists. The story you live depends on how your brain sews events into a line and calls it the present. Why do terrifying seconds feel longer, while birthdays seem to arrive faster each year? The brain doesn't run on the clock on the wall. It has its own way of stitching experience together, and when that stitching changes, the length of a moment stretches or collapses. That's the hook, and it points at something uncomfortable. Your sense of time is built after the fact, then handed to you as if it were live. Start with how the brain builds a now. Sensory signals don't arrive in sync. Light hits the eyes first, sound lags. Touch depends on limb length and nerve speed. To make the world feel coordinated, the brain holds an integration window, roughly 1/10 to 1/3 of a second, and waits. It collects what just happened, aligns it as best it can, and then releases a single present. This small pause, imperceptible most of the time, creates a single coherent scene out of events that did not line up in real time. The cost for this coherence is delay. The payoff is a stable world. Temporal binding tightens this bundle. When one event appears to cause another, the brain pulls them closer together in perceived time. A button press and a beep feel more simultaneous when you expect the beep to follow. That compression reduces the jitter between cause and effect and gives you the sense of a smooth stream. If the beep occurs without your press, you notice a gap. If you press without a beep, the same. But when cause and effect belong together, the brain shrinks the interval to keep the story tight. Predictive processing pushes further. The brain uses past patterns to guess the near future, then compares guess to input inside that integration window. Correct guesses move forward with little fuss. Surprises get flagged and can shift how long a moment seems to last. This constant alignment means the now you live in is partly a model. It's not a snapshot taken at a single instant. It's a best estimate built from what just happened and what usually happens next. That estimate can be probed. In classic lab work on decisions, a slow buildup of neural activity, the readiness potential, rises before people report choosing to act. The reported choice trails the brain's preparation by a few hundred milliseconds. However you interpret that, it shows conscious awareness is late to its own party. Awareness doesn't light up at the first neural whisper. It arrives after partial assembly, folded into the final scene as if it had always been there. Stress warps the assembly process in a different way. During danger, attention narrows and arousal spikes. The brain samples more details per unit time, writes denser records, and later those moments feel long. People in emergencies often report that seconds felt stretched. The experience isn't about the external clock. It's about how much was encoded per slice of the integration window. More detail per slice means more slices when you look back. So the episode feels thick. Dreams pull the lever the other way. A full arc, travel, conversation, conflict can feel complete even though it played out over a few minutes of REM. The brain builds coherent scenes without the usual anchors from the outside world. When you wake, the lack of external timestamps collapses the duration. The narrative felt dense while dreaming. When recalled against the morning's steady cues, it compresses. The story survives. The timing doesn't. Temporal binding backs this up. When two events belong to a single action plan, like moving your hand and hearing the tap, the brain ties them together. When they don't belong, it lets them drift apart. Across tasks, the perceived gap follows these expectations more than it follows raw timing. Shifts in binding strength change how you judge the order of events, not because the order changed in the world, but because the brain chose a tighter or looser stitch. The role of neurochemistry shows up in everyday timing. Systems that use dopamine and norepinephrine tune how we track intervals. Changes in these systems can make seconds feel too fast or too slow. Drug studies, clinical findings, and basic neuroscience point in the same direction. These chemicals adjust how quickly internal clocks tick and how much attention locks onto a stimulus. Under high norepinephrine, you attend more, sample more, and time stretches. With altered dopamine, intervals can expand or slip, and tasks that rely on steady timing become harder. Age adds another layer. As we get older, Routine fills more of our life, attention scatters across many tasks, and memory stores fewer distinct markers for a day. The brain anchors subjective time in how many notable events it encoded. A day with fewer novel anchors compresses in retrospect. Weeks with repeats compress further, so the calendar pages turn at the same rate, but the memory density thins. The felt speed rises because recall runs on a sparse index. This lagged, edited process can be measured in small illusions. Tap your finger and see a flash. Depending on expectation, the flash can feel earlier or later than it was. Close timing judgments wobble because the system responsible for aligning the senses is designed to favor consistency over raw arrival times. That same design means that when your model predicts a sound after a tap, you perceive the sound as closer to the tap, even if the lab delays it. The smoothness comes from compression that creates tension. If now is assembled, then the flow you feel is not raw physics. It's a user interface. The interface can be compelling and mostly reliable, but it is not the thing itself. The lag can hide itself most of the time, but under pressure, it shows. It shows when seconds dilate during a crash. It shows when you wake from a dream that seemed long. It shows when a prepared decision rises before awareness and slips into the story as if chosen on the spot. There's also the forward lean of prediction. When the brain expects the next note in a melody, it primes the motor and auditory systems in advance. Hearing the note confirms the guess, and the moment slides by with little perceived effort. Miss the note, and your sense of time stutters. You feel the glitch because the brain must restitch the sequence. The annoyance when a beat is dropped lives in that restitching. Your sense of flow depends on fewer repairs. Tie this back to stress. The emergency that slows time also imprints stronger memories. Later, those memories expand the event. What felt slow in the moment gains even more apparent length in recall. And the opposite, calm routine, leaves fewer distinct traces. Later, you compress it even further. The instant-to-instant mechanism and the long-term memory mechanism both push perception in the same direction. Novelty stretches, repetition shrinks. The readiness potential story invites pushback. Some argue the timing of reported awareness is tricky. Reports require metacognition, and the way we ask can shift answers. But even when critiques are addressed, you still find the gap between preparation and conscious access. Some part of the decision process unfolds below the threshold of the story you tell yourself. The lag isn't a flaw in a single paradigm. It's part of the brain's design to batch and release experience in cohesive packets. This is where the editor analogy earns its keep. Think of a producer buffering short clips before going live, adding a half-second delay to catch and fix glitches. The editor speeds or slows playback to keep the show smooth when the stream is noisy. Attention is the hand on the slider. Arousal is the gain. The output is a continuous feed, but it's been trimmed, shifted, and occasionally stretched to keep coherence. We live in that broadcast, not in the raw feed. Chemistry adjusts the controls. Changes in dopamine and norepinephrine move the slider for interval estimation and the dial for how narrow the integration window becomes. On tasks where you tap in time with a beat, small shifts in these systems alter your accuracy and your confidence. In states of low novelty and diffuse attention, the editor buffers fewer highlights and the highlight reel shortens. On days loaded with sharp cues, the reel grows. None of this says external time is fake. It says the felt stream is not a direct readout of it. The brain edits before handing off awareness, then memory edits again on replay. That two-stage rendering is why your life can feel too fast and too slow in the same week. It's why a vacation seems long while you're on it, then short when you look back 6 months later. The moment-to-moment editor widens the window for new sights. The long-term archivist compresses the file. If the brain already edits the order of events to keep coherence, then physics may not need a special now to explain why we feel the present. The sense of passage could emerge from internal bookkeeping rather than from a universal flow. The lab can reveal the lag. The street reveals the bias. Together, they point at the same answer. The story of time in your head is a construction. That brings a small payoff. Our experience of time passing is a cognitive rendering. It does useful work. It coordinates senses, aligns actions, and helps us plan. But it is not proof that the universe itself is stepping through frames. It's proof that a brain prefers a tidy scene over a perfectly timed but jagged one. And since the brain can blur before and after to keep the scene intact, it's no surprise the smallest experiments in physics find edges where order flips and our intuition falls off. We've already seen what happens when a choice seems to echo backward. Let's go back to that edge and push the question of before and after as far as experiments allow. Can the universe keep order with no master clock in charge? We've already seen quantum experiments bend the idea of before and after. So let's strip away the ticking and ask what's left. What if causality is not a line that events stand on, but a rule book that governs which correlations are allowed to show up together? In that view, order is not the schedule. Order is the set of constraints that patterns must satisfy to be possible at all. Start with the most protective rule of them all. No signaling. Quantum entanglement gives you tight, instant correlations, yet it never lets you use them to send a message faster than light. If you and I share entangled particles, my choice of measurement cannot encode a readable bit for you at a distance. When you collect your outcomes alone, you see random noise. Only when we compare notes later do the correlations appear. That simple fact keeps the peace between quantum theory and relativity without calling on a global timestamp. The universe says yes to certain joint statistics and no to others, and that no is enough to block paradoxes. Next, take a wider view of how histories form. Instead of a single unfolding timeline, the consistent histories approach assigns probabilities to whole sequences of events, but only to sets that don't interfere with each other. If two candidate histories would overlap in a way that produces quantum interference, you're not allowed to treat them as alternative classical stories. The rule is strict. Assign probabilities only to mutually consistent families. This restraint prevents contradictions before they arise. It's not that the cosmos flips through a book of definite pasts and futures. It refuses to bind them into a single narrative unless the mathematics says they can coexist without conflict. Now push order itself to the edge. In the process matrix framework, you can have situations where the causal order between operations is not fixed. The system behaves as if A influences B and B influences A in a superposition of orders. This is not chaos. Probabilities still add up. Signals still cannot break the speed limit. What changes is our old assumption that every pair of events sits within a single before and after relation. In demonstrations of the quantum switch, two tasks act on a target in no definite order, yet the device yields well-defined, repeatable outcomes. The tasks don't scramble into nonsense. They obey a higher-level consistency rule that forbids patterns that would let a message loop into its own origin. The result hints that causality can be local, contextual, and yet fully coherent without a master time ordering the play. If that feels slippery, think of a board game whose rulebook bans illegal patterns, regardless of move order. You and a friend can choose the order of your legal moves or even randomize it, and the game still makes sense because the rules restrict what states can occur, not which must come first. The board never needs a clock to keep score. The constraint structure does the work that, in classical thinking, we outsource to time. In quantum setups with indefinite order, the physical rules are the no-go patterns encoded in the theory's allowed correlations. This perspective reaches into how we model cause and effect. In classical statistics, causal modeling frameworks draw arrows between variables, define interventions, and diagnose which variables influence which. When adapted to quantum settings, those ideas still help, but the arrows can no longer be universal and linear. Interventions disturb quantum states in ways that depend on context, and measurement choices help define which causal relations even make sense. You can still ask counterfactual questions. What if we change this setting? But your answers rely on the family of compatible operations you've allowed. Outside those families, the very question may lack meaning. The limit here is not a failure of logic. It's a sign that causal talk must respect quantum constraints from the start. What about the fear that, without time, we fall into grandfather paradox territory? Messages sent to the past, loops of cause that erase their own source. The no signaling rule already blocks the cheapest routes to trouble. More deeply, the consistent histories and process matrix approaches disallow the probability assignments and correlations that would make contradictions statable in the first place. You never get a set of statistics that both implies a message reached its own sender before it was sent, and also that the sender could exploit this implication to change the setup. The universe seems to maintain a kind of logical hygiene. The conditions that would generate a paradox never appear together in the same experiment's data. Experiments on indefinite causal order strengthen that point. The quantum switch is a device where two operations, call them A and B, act on a system in a superposition of orders. If you try to force the data to fit a fixed order, the model fails. Yet the outcomes are clean and reproducible. They show advantages for certain information processing tasks, not because time runs backward, but because the constraint structure of quantum processes is richer than our classical metaphors. The device demonstrates that which came first can be undefined, while what is allowed stays sharp. That's order without a timeline. Now bring in the worry that all of this is sleight of hand. If we say correlations enforce causality, are we just hiding the clock inside the math? The test is whether these constraints predict outcomes across different contexts without an underlying hidden schedule. They do. When you vary the operations in an indefinite order setup, the allowed joint probabilities still respect the same rules. When you trace out parts of an entangled system, the no signaling conditions still fence in what local observers can see. The stability of those fences across scenarios is what you'd expect if the rules are fundamental and not a workaround. There's another angle. Sometimes asking what caused what has no unique answer because that question smuggles in a particular time slicing. Without a global clock, you should expect different observers or different experimental decompositions to disagree on a single absolute order. What they agree on are the invariant constraints. No faster than light signaling, no probabilities that violate the structural consistency conditions, no closed loops of usable information. Agreement lives in the border walls, not in the storyboards we draw inside them. This constraint-first view also explains why entanglement feels both powerful and harmless. It generates correlations no classical model can reproduce, yet it cannot be harnessed to send a controllable bit instantaneously. You get surprise without leverage. That's a design feature. If entanglement allowed both non-classical correlations and superluminal control, contradictions would follow quickly. The fact that we only get the first is a clue that the causal architecture is tuned to be expressive and safe at the same time. Now consider the frontier where even the idea of a reference frame starts to blur. If a clock is put into a superposition of heights and gravity shifts rates by height, then even the relative phase that marks how far the clock advanced becomes entangled with geometry. If that setup were taken to the limit, the very question of which event came first could lose its single answer. Not chaos, just a thicker web of correlations with the same rules refusing forbidden patterns. A skeptic might ask, if there's no global time, how do we compute, predict, or control anything? The answer is local structure. You pick a consistent set of operations, define your interventions within that set, and the theory gives you well-behaved probabilities. You don't need a master schedule to plan a mission with quantum sensors or to certify that a communication protocol doesn't leak information. You need the rule book that forbids illegal joint distributions and quietly permits the rest. The practical payoff shows up in tasks where indefinite order helps. Certain computations or communication schemes become more efficient when the order of operations is not fixed. That advantage doesn't violate causality. It uses the broader menu of legal correlations. Think of it as access to moves that a classical referee would mistakenly ban because they don't fit a single timeline, even though they obey every deeper constraint. So the fear of paradox gives way to a more modest challenge. Don't ask for a single timeline to underwrite every phenomenon. Ask for coherence conditions that all observers can check. If those conditions hold, no signaling at the margins, consistency of probability assignments, and adherence to the allowed process structures, then causality has been enforced by the shape of correlation space itself. This shifts how we talk about explanation. Instead of A caused B, then B caused C at these times, we can say the allowed joint statistics make A and B interdependent in this way and forbid patterns that would enable contradictions. The sense of flow is optional. The logical order, enforced by constraints, does the heavy lifting. Where an arrow appears, it is the outcome of boundary conditions and the choice of what we treat as interventions, not the decree of a cosmic clock. And right at the horizon of this story sits gravity. Our best clocks are quantum systems, and gravity shifts their rates. If those clocks are entangled, gravity has to act on their phases and correlations, not just their tick rates. That hints at a world where causal structure depends on geometry and quantum state together. If clocks are participants in the game, not outside observers, then the rules must account for how geometry and entanglement co-author the order we see. So we arrive at a compact claim. The universe can keep order with no master time by enforcing a tight set of correlation constraints. That's enough to block paradox, guide prediction, and even power new kinds of information processing. And if gravity touches the internal phases of clocks, then the next step is clear. Bring gravity into the quantum lab and watch timekeeping become part of the dynamics, not just a way to read them. What if two clocks didn't just tick at different speeds in gravity, but picked up different quantum phases that could interfere with each other later? That would mean gravity isn't only stretching or shrinking rates. It's changing the very angle of a clock's rhythm and doing it in a way that can be added, cancelled, or shared. The weird part comes when the clocks don't stay separate. If they're quantum, their phases can tangle. Your choice of what to compare and when can pull a pattern out that wasn't visible to either clock on its own. The question stops being how fast time runs and turns into what counts as time when the tick itself is part of a wave. Here's the setup. A quantum clock is any system whose internal state accrues a phase at a stable, known rate, an atom with two energy levels, a trapped ion with a well-defined transition, or a photon's polarization playing the role of a hand that rotates on a tiny dial. In a gravitational field, that phase doesn't build at the same rate everywhere. A small change in height shifts the redshift factor, so two identical clocks placed centimeters apart gather different phases. The classical version of that effect is time dilation. The quantum version keeps the phase coherent, so those differences remain superposed and can interfere. Now match two such clocks and let gravity act while they stay quantum. If they start entangled, the redshift produces correlations between their phases that you can't assign to either one alone. Pull on one side and the other responds in the statistics. That is where tension enters. If clocks are quantum objects, gravity doesn't merely shift time as an external backdrop. The geometry that sets redshift also controls phase evolution, and if the clocks share entanglement, geometry turns into a partner in their joint dynamics. You can't describe each clock's flow separately without throwing away information. Bring them back together, and the interference tells you that evolution and geometry are coupled. The usual separation between the stage and the actors blurs, because the stage adjusts the actor's timing, and the actors carry records of that adjustment in their shared phase. In the lab, the effect starts small but clean. Optical lattice clocks based on strontium transitions can resolve frequency shifts from a height difference of millimeters to centimeters. Place one clock slightly above the other, and you get a measurable gravitational redshift. Keep coherence long enough, and you can bring their phase reference back together to see fringes. Experiments with trapped ions push this further. An ion's internal transition acts as the clock hand, while its motional state sets a reference. Spatially separate two ions or two wells at slightly different heights, prepare them in a joint quantum state, and let the field act. After a set time, recombine and read out the relative phase. The shift follows the predicted gravitational potential difference. What matters for our story is that the phase isn't just a rate change logged independently by each ion. It's a shared, testable quantity that shows up in joint measurements when coherence is preserved. Proposals and early demonstrations go beyond simple redshift by tracking how coherence degrades when gravitational potential varies across a superposed state. If a clock's wave function spans two heights, the phase accrual differs across branches. When later recombined, those branches can partially dephase. Make two clocks share entanglement before the wait, and gravity generates correlations that you can only explain by saying the clocks in the field formed a joint system. As techniques mature, researchers aim to show scenarios where gravitationally induced phase differences entangle initially independent clocks, or where the presence of mass modifies interference visibility through coherent coupling rather than noisy disturbance. These aren't one-off glitches. They follow from treating timekeeping as quantum evolution under a Hamiltonian that includes gravitational potential. A simple analogy helps with a warning that it's only a guide. Think of two metronomes sitting on a slightly flexible surface. If the surface bends under their weight, each metronome's beat shifts a little, and the bend depends on both. Over time, their ticks drift out of phase. If you place them back on a rigid table and compare, you find a beat pattern that reflects not just their isolated history, but also the way the surface responded to them together. In the quantum case, the surface is gravitational potential that sets phase accrual, and the beat is a phase you can interfere. The crucial difference is that quantum phases can be superposed and entangled. You can set up the metronomes so that some combinations of outcomes cancel and others amplify, revealing the shared response without ever seeing individual ticks directly. This line of work nudges a larger point. If entanglement patterns define what counts as a clock for internal observers, gravity's effect on those patterns is not an afterthought. It is part of the definition of temporal order within the system. Make the clocks better, higher Q, narrower line width, longer coherence, and you feel gravity more strongly, not because the field grew, but because your phase sensitivity rose. The more precisely you try to separate the time that passes from the geometry it passes through, the more their joint nature shows up in the statistics. In this view, you can't split the passage of time from the gravitational environment. The tick is inseparable from the shape of the field, and the field at the quantum level is inseparable from how energy and information weave through the system. Push this picture towards strong fields and you reach puzzles about black holes. If gravity can entangle clocks, then an extreme potential should not merely slow an outside observer's time. It should restructure which subsystems can serve as good internal clocks at all. That shift ripples into questions about how information flows during processes like evaporation. If state evolution depends on clock entanglement, then following the time of evaporation means tracking which degrees of freedom carry reliable phase references and how gravity modifies their correlations step by step. This doesn't solve the puzzle on its own, but it reframes it as a problem about maintaining or redistributing coherent timing inside a changing gravitational network. Seen from the ground up, time emerges where conditional probabilities create an effective evolution between subsystems. In many body settings, that evolution takes on the flavor of a Schrödinger equation for parts that use other parts as reference. Gravity then adjusts the mapping between those internal times by imprinting redshift into the phases. When subsystems become entangled in the presence of gravity, their joint state encodes a web of relative phases. Read along one thread and the other seems to evolve accordingly. Because the whole state can be static, the appearance of motion depends on which correlations you condition on. A lab clock that drifts nanoseconds per day under gravity tells you the principle at macroscopic scale. An entangled pair whose interference fringes bend under a height difference shows you the coherent, microscopic version. This makes a broader claim plausible. The geometry that we usually treat as prior might be a summary of entanglement patterns among quantum degrees of freedom. If so, the redshift that shifts phases is not a cause from outside, but a feature of the information structure. Distance and curvature would then be ways to encode how hard it is to keep phases aligned across subsystems. Tensor network models and holographic arguments hint that spatial relationships can be reconstructed from patterns of entanglement. Translate that to clocks, and you get a picture where time is the shadow cast by how information flows along those connections. When entanglement changes, what you call time changes with it. The anticipation builds here for a reason. If geometry comes from entanglement, and clocks owe their ticks to geometry, then time is downstream of correlation. Our most precise timepieces, which keep a second within a span longer than the age of the cosmos, are not just passive observers. They are probes that couple to the field and then talk to each other through shared phase. In these experiments, you can watch timekeeping turn into a test of the weave itself. Change the potential by a centimeter. Flip a joint state from product to entangled. The visibility of the fringes and the alignment of the phases tell you how the environment stitched them together. What used to be a rate difference becomes a diagram of who is synchronized with whom and why. Here's the payoff at this stage. Clocks don't only measure time in this framework. In a quantum gravitational sense, they help define the spatiotemporal scaffold by carrying and exchanging phase information. The better they are, the more their phases act like threads that tie regions of the system into a consistent story. If you remove the clocks or decohere them, the story blurs. Add them back and the structure sharpens. That doesn't mean time pops into existence from nowhere. It means the role we assign to time is the role of a pattern we can read off from entanglement and gravitational response. The laboratory advances from centimeter-scale redshift in coherent atoms to interference experiments that preserve phase long enough to see gravity's imprint give that claim teeth. So we return to where this episode has been pointing. If gravity can tangle clocks, and if the phase they share is the real content of timing, then now is not a universal stage direction. It's a relation inside a network that bends with mass and energy. A still universe can carry moving stories when you read along those relations, and the more carefully you read, the more the background looks like a product of the story rather than its frame. Which brings us to the part that matters beyond the lab. If the world is complete without a master time and our best clocks are participants in the order rather than outside judges, then meaning has to live in how those participants connect. That is where the next step leads. A universe serene in its completeness, and minds that find motion not in flow, but in the way connections light up. If every moment already exists, memory stops being a trail we leave behind us and becomes a way of landing on certain pages. Death stops being a cliff and becomes a location in a landscape. The horror comes from feeling pushed toward that location with no way back. But what if there is no push, just the fact that some pages contain us and some do not? In a world without a flowing time, memory is not a real running. It's a selection rule. Your brain holds records, neural patterns, synaptic strengths, physical traces. Identity is the web that links those records into a coherent scheme. When you think me, you are not traveling. You're reading a consistent set of records that point to earlier records in the same configuration space. Continuity isn't motion, it's alignment among stored marks. The marks ground the sense of having been, and they live side by side with the marks of what you call now. Fear rises because we feel dragged from what we love into absence. Timelessness reframes that fear. Loss is real, but it is not a vanishing. It is the fact that some configurations contain the person you miss smiling at the table and some do not. The ache belongs to configurations where that absence is recorded. The warmth belongs to ones where presence is recorded. Both exist. The flow between them is the story we tell when we splice records into a timeline. Without flow, relation remains. The relation is not weaker than motion. It is the structure that motion hints at. Think of a lifetime as a mosaic already complete. Each tile is a now, containing all the records and relations that make it what it is. The tile with a child's first step is there forever. The tile with a last breath is there too. Grief and joy do not cancel each other out across tiles. They are real within their own locations. The person you love is not smeared thin across time. They are sharply present where they are present. The absence you feel later is just as sharp where it appears. Our language prefers verbs, so we say that we move through those tiles. But the tiles do not shuffle. The story is the path we draw after the fact by following the chain of records that point forward and backward within the mosaic. Philosophers who study eternalism describe this fixed landscape and argue that personal identity is made by psychological continuity, by overlapping chains of memory, intention, and character, rather than a single bead sliding along a thread. Clinical work on memory shows that remembrance is reconstructive. Each act of recall rebuilds the scene using stored fragments, context, and present goals. So the felt past is not a pristine recording. It's a selection and a reassembly that happens in certain tiles. That does not make those past tiles unreal. It means that the link from this tile to those tiles is built out of records and rules, not a metaphysical conveyor belt. If this is unnerving, consider a plain analogy. An album gets printed. Every page is already there. Love is on the pages where it appears. The page where you meet someone is alive with meaning in that location forever. The page where the hospital room is quiet after the machines stop is also fixed. Turning the pages does not change what is printed. It only changes which page your eyes scan. The turning is how our brains sample the album. Even if the pages do not move, your focus does, by virtue of record-to-record relations that define which page refers to which other page. This stillness does not void responsibility or planning. The thermodynamic arrow still constrains what can be done inside many tiles. Local pockets of low entropy contain reliable engines for making records, doing work, and changing configurations in specific ways. That arrow shapes ethics because it sets real limits on what future records can contain, given what present records allow. Action matters because some tiles contain you taking steps that create downstream records, and some tiles contain you not taking them. Both sets exist, but the chain your records indicate from this tile points toward one set and not the other. That is what you experience as choice and consequence. It is not illusory in the pejorative sense. It is a structural fact about how records link. The worry that meaning drains away in a fixed universe rests on the idea that value needs becoming, but meaning can live in relations. A melody is not the motion of sound through time if the score is already complete. It is the structure of intervals and harmonies spread across the page. Performance makes the structure audible in sequence, but the value lies in the pattern, not the turning of pages. Likewise, your life's meaning is the structure linking the moments where you loved, learned, failed, repaired, and tried again. That structure does not require a universal clock. It requires consistency among the records that house your values and actions. What about death? If time does not flow, I will die becomes, there exist pages where I am alive, and there exist pages where I am not. The fear remains inside the pages where that anticipation is felt. The kindness you showed at a bedside exists in every page where it happened. The conversations, the small rituals, the ordinary afternoons, each is fixed where it belongs. Death is not erased, and neither is the life that leads up to it. The block contains all of it. For the bereaved, the knowledge that the pages with laughter are not annihilated can soften the sense of cosmic theft. They remain present in the only way anything is present in a timeless landscape, as stable structures. Memory's reconstructive nature also explains why the present feels unique. The brain samples inputs, stitches them into a coherent scene, and anchors the scene to stored records. The subjective now is the result of buffering and prediction, not a beacon moving along a line. When stress floods the system, the sampling rate and weighting shift, stretching the felt length of a moment. When years accumulate, we compress repeated patterns and store fewer distinct markers, so the span feels shorter. These are features of the editor, not the film. They tell us how the album is read, not whether it was printed. Meaning does not require motion, but it does ask for order. What holds the stillness together is the network of lawful correlations, physical constraints on which records can coexist. The mind's stories are nested inside those constraints. A promise matters because there are pages where the promise exists alongside later pages where the kept or broken promise leaves consistent records. The moral weight you feel comes from those patterns. They do not need a cosmic current. They need coherence. There is a common objection. If all pages exist, why prefer kindness to cruelty? Because within the family of pages that your records connect to from here, the ones in which you act kindly have downstream structures that align with your stated values and reduce harm as measured by the records of others. Ethics is local and structural. It is not negated by the presence of other pages with different outcomes. You don't control the album, you control which family of pages your current records point toward as you act. That control is limited by physics and circumstance, but it is real within those limits, and it is what we ordinarily mean by agency. Another worry is whether grief is somehow less valid if the lost person remains present on their pages. It isn't. Grief is a record that shows up in specific pages and forms part of the structure. It confirms that the relation between those earlier pages and these pages matters. It is not an error to mourn. It is a recognition that some configurations no longer include a living conversation partner, even if the pages where the conversation happened are intact. The reality of the earlier presence does not cancel the reality of the present absence. Both truths can be held at once because both are parts of the same fixed whole. This perspective can change how we plan. Instead of treating the future as empty and waiting, we treat planning as aligning present records with preferred downstream patterns permitted by the local arrow. You set goals, not to build a future from nothing, but to occupy a path of pages where those goals' records exist. That framing sounds abstract, but in practice, it looks like ordinary life. Writing down intentions, arranging reminders, shaping environments, and building habits. Each step is a way of increasing the likelihood that the chain anchored in today leads to the family of pages consistent with your aims. If meaning lives in structure, we can look for it in the regularities that hold across our pages. Friends who know your stories link their pages to yours, increasing redundancy and resilience of the records that define your identity. Communities formalize shared intentions, creating stable structures that live in many minds and many rooms. These are not metaphors. They are the literal distribution of records across pages that makes a life bigger than one skull. When we say that someone lives on in the memories of others, we describe a physical fact about stored patterns. This is not a call to detach. It is an invitation to see value as something that doesn't need a river to carry it. The relief some people feel when they first grasp the block view is not apathy. It is the easing of a background panic about slipping. You still care, you still act, you still love. You just do it without thinking that meaning depends on a clock's sweep. The sweep is part of how the mind reads. The caring is part of the pattern. If all this feels austere, it can also be quieting. A universe serene without time does not belittle our inner life. It frames it. The pulse you feel, the urge to hold on, the stories that bind your days. These are features of how certain pages are built. They matter within those pages because you matter within those pages. What holds the stillness together is not sentiment, it is order. What gives the stillness warmth is not motion, it is connection. So we turn toward that mirror. The world may be timeless in its foundations, and yet minds learn to move within it, tracing paths of care and meaning through a complete landscape. The next step is to ask what kind of architecture could underwrite both stillness and story at once, and how far that quiet order can reach. If time isn't fundamental, what is doing the organizing? Something has to keep the universe from turning into noise, and the surprising answer many physicists explore is structure itself, not motion, not a ticking background. Patterns of entanglement and constraints may quietly hold everything in place, the way grammar orders a sentence without any stopwatch. That's the hook, order without a clock. Start with a sober idea. The holographic principle says a region's information can be fully accounted for on its boundary. Think of it as a rule that the interior doesn't need extra data beyond what the surface already encodes. It isn't claiming a visual trick. It is a statement about bookkeeping for quantum information. Within that frame, space-time looks less like a stage and more like a way we read correlations. If the boundary already contains the script, the bulk we move through could be a decoding of that script, and before and after might be features of how we parse it, not ingredients of the script itself. One concrete arena takes this further. A duality relates a gravity theory in a curved space with negative curvature to a quantum theory on its edge. Distances in the interior map to entanglement data on the boundary. In practice, that means separating a boundary system into pieces and asking how entangled they are can recover geometric features like areas and separations in the higher dimensional description. Geometry is no longer primitive. It becomes a translation of correlation strengths and patterns. If a distance can be reconstructed from information, the need for an independent time variable starts to feel less necessary. Temporal order could be a way we arrange outcomes in a useful sequence, while the underlying object is a web of relations standing all at once. To make this less abstract, consider tensor networks, tools that represent quantum states as nodes connected by bonds. The widths of those bonds track entanglement. When arranged in certain patterns, these networks reproduce properties of curved spaces. You don't input a metric. The network structure gives you one. Change how the entanglement is distributed, and the space warps accordingly. No clock is running inside the network. Everything sits there, static, but the arrangement itself dictates what an observer would call geometry and potential dynamics. You can slice the network along different paths and read out an effective time evolution, but that evolution is a choice of how you traverse the static object, not an intrinsic heartbeat. This raises a natural worry. If no fundamental time exists, how do we predict anything? Science relies on forecasting, on linking conditions to outcomes. The answer inside these frameworks is correlation constraints. When correlations are rigid enough, they severely limit which joint outcomes are allowed. That restriction yields reliable patterns we mistake for temporal laws. Think of it like a crossword. The grid and clue set rule out almost all letter combinations. You don't need the puzzle to unfold in time for it to be solvable. The constraints already decide what fits. Similarly, a universe can be lawful because its static correlations are consistent, tight, and richly structured. The Ryu-Takayanagi relation gives a quantitative handle. It links the entropy of entanglement for a boundary region to the area of a minimal surface in the interior. If the interior's areas are calculable from boundary entanglement, then what we call shape is a reflection of informational ties. Shift which degrees of freedom are entangled and by how much, and the corresponding surface area shifts. That mechanism doesn't need an external clock. It needs only an assignment of which parts of the system are correlated. In that sense, time may be a shadow cast when we track how these assignments differ across slices we call states. Some proposals even tie connectivity itself to entanglement. The thought here is that relationships between subsystems, being entangled rather than independent, may be the source of being near in a geometric sense. Two regions deeply entangled on the boundary behave as if a short bridge connects them in the interior description. Thin out the entanglement and the bridge lengthens. Remove it and the regions drift apart, not because they moved, but because the pattern that defined their closeness changed in a different description. Connectivity from correlation replaces proximity from position. No clock needed to define the link. The link is the condition that makes a clock plausible. But these are frameworks, not settled facts. They depend on special settings, idealized boundaries, and symmetric spaces. They haven't yet delivered a full map to our universe with all its quirks. Even so, they show a path by which order arises from static structure. You can reconstruct distances, areas, and in some setups, even aspects of dynamics from unchanging patterns. That's enough to make the idea of emergent time more than a metaphor. It becomes a technical program. Derive the feeling of flow from the mathematics of correlation. If structure can hold space in place, what about arrows? Thermodynamic arrows often appear when we step back and lump details together. Coarse graining hides microstructure and reveals trends. Entropy tends to increase, information tends to spread from localized pockets into the surroundings, and useful work gets harder as records proliferate. Those arrows don't require an external master time either. They require asymmetry in the way records and correlations are distributed. When you choose a macroscopic description that forgets most degrees of freedom, the observed direction of change pops out as a statistical feature of the pattern. Tight constraints plus incomplete descriptions yield the sensation of before and after. There is a useful way to think about this. Consider a woven fabric. The strength doesn't come from threads racing along the loom. It comes from the pattern of crossings, how each strand locks with neighbors. Pull on one edge, and the force travels because the pattern channels it, not because the threads are moving of their own accord. In the same way, predictions in a timeless framework come from reading the weave of entanglement and the constraints it enforces on outcomes. We experience that as a sequence because our minds and instruments pass the weave in ordered slices. If this still feels slippery, return to the starting mystery. We saw a measurement choice correlate with what looked like past behavior. In a structural view, that isn't a message from the future. It's a global consistency condition across the whole setup. The correlations are stitched so that certain combinations appear together and others never do. When you change a knob later, you're selecting a different cross-section of the same static weave, and the earlier record aligns with it because inconsistent combinations were never part of the allowed pattern. The timeline is our way of narrating a constraint satisfaction problem. None of this removes the burden of making contact with real data. These ideas must explain why clocks drift in gravitational fields, why particles interfere, why heat disperses, and why observers agree on stable regularities. The progress so far hints that we can recast those phenomena as consequences of information structure. Holographic dualities give formulas tying geometry to entropy. Tensor networks show how metric-like features follow from entanglement layouts. Coarse graining creates arrows that match thermodynamic experience. Put together, they sketch a picture where lawful behavior arises without a master time parameter. That picture also connects to how we compute. To predict, we don't need the universe to evolve in our simulation. We need a rule that picks allowed configurations and a method to assign weights or probabilities to them. Dynamics appears when we compare neighboring configurations along some chosen axis. Choose a different axis, and you can get an equivalent story with a different time. The underlying object didn't change, our slicing did. What remains fixed is the constraint web that keeps contradictions out and lets reliable patterns in. It's worth stressing the limitations. These frameworks are not yet universal. They rely on assumptions that may fail outside special cases. Some key results live in toy models far from the messy universe we observe. And the exact mechanism by which a unique, shared sense of time emerges, so that clocks agree enough for technology to function, remains under development in this language. That open space is where current work focuses, identifying which structural features guarantee robust, approximate time for subsystems like us. Even with those caveats, the lesson stands. You can get order from relation alone. If geometry can be read from entanglement, and arrows can be read from coarse descriptions and information flow constraints, then a clockless foundation can still support prediction and explanation. Structure is enough. Not because it waves away difficulty, but because constraints leave so few consistent arrangements that regularities become unavoidable. So we loop back, the particle that seemed to look back. The equation where the symbol for time never appears. The human heartbeat that seems to mark a flow. Underneath, a quiet architecture of correlations may be doing the heavy lifting, giving us space, shape, and sequences as ways to navigate a static web. That web doesn't need to move to be lawful. It needs to be consistent. Rest there for a second. If the weave is what holds everything together, then resisting the lack of a fundamental clock is like resisting the rules of grammar because sentences don't come with a metronome. The order is real, even if the ticking isn't, and that suggests a way to live with the idea. Learn the pattern, trust the structure, and let the story play across the weave without insisting on a river beneath it. The deepest code we have works without a clock. Equations that describe the whole do not need a ticking variable, yet inside their fixed web of correlations we find rhythms that act like hours and seconds. From a static state, we read consistent sequences, and those sequences become causes and effects. A detector clicks after a preparation, a heart rate steadies after a breath, a memory follows a choice. The order does not come from a universal hand pushing events forward. It comes from constraints that let only certain patterns line up and forbid the rest. Meaning, then, is not a function of passage. It comes from structure and connection. We locate ourselves where records agree, where signals cohere, where correlations form a stable thread. The stories we live are ways of navigating that thread. We experience a moving present because we sit inside the weave and sample it from one conditioned slice to the next. When the samples line up, We call it a life. If that quiet view steadied you, subscribe and share what the word now means to you. Your reflections shape where we explore next. Say how you sense it when you wait, when you create, when you sit with someone you love. Say what changes when now is not a knife edge, but a relation among records. Then let a question hang. If motion is a feeling and order is the fact, where do freedom and responsibility root themselves? If the future already has a place in the pattern, what exactly does a decision do? Perhaps the right search is not for a cosmic second hand, but for the rules that make certain stories possible and others impossible. Perhaps the next step is to stop asking the universe to tick and start asking how to read it.